Hi, this is continuation for power electronics lectures, and today we are going to start talking about DC to DC converters. In the previous lectures, we covered lots of topics about switches and their thermal considerations, power losses, and other related topics to inverters. And today we are going to go for popular topic about DC to DC converters. So we have talked about before the difference between linear operated systems and switch operated systems, and we concluded that the switch operated systems brings to us more efficient circuits and systems, and we have here less losses than the linear operated systems. However, in this circuit, for example, if we have a load here and we have a switch here and we are pulsating that switch to produce a different average voltage according to the duty cycle, the load is still seeing different average voltage, and that achieves the objective of generating different voltages across the load. But the question is, are all the loads happy with this kind of output, pulsating output voltage and pulsating output current? The answer will be no. For example, if this one is a heater, yes, it has no problem of delivering pulsating output voltage and current because the heater has an inertia, and that inertia is big, and it takes time to respond to this pulsating, and it has no problem with this. However, if we have a microprocessor here or very sensitive load, the pulsating output there is not very desirable. So the scientists now start looking for different additions and different topologies to increase the efficiency of this topology with satisfying the loads requirement. So one of the things that they start looking at, which is the using the switching circuits, which relies on the inductors and capacitors ability to store and release energy over the switching period. So we have on and off here, but they rely on some capacitors and some inductors in the way to store the energy and prevent this kind of off period here of the voltage and current. And this is the start of DC to DC converters. We know when we try to change the inductor current, this inductor will resist the change and produce some voltage. But if the current is not changing at all at steady state, so there is no voltage. So in DC systems and DC circuits, at steady state, the inductor behaves like a wire, and the voltage across it is zero, which is the VL here, because VL equals LdI by dt, and at steady state, there is no change in current, so VL will equal zero. But why we mention this? Because in switch circuit where we have PWM and we always switch on and off the voltage and current, does the voltage still equal zero in switch circuit? For example, if we have this waveform, which is a result of one of the DC to DC converters, okay? So the inductor current will try to rise, will try to fall, rise and fall, rise and fall, and the voltage at the same time equals some different values over time. So the question is, does the voltage equal zero at steady state? The answer is yes for the average value. So the same concept is applied also in switching circuits where we have this kind of inductor current and voltage. The average voltage across an inductor over a complete switching cycle in the steady state is zero. So yes, it equals zero, but not the instantaneous voltage, but the average voltage over a complete cycle over T here. So the average voltage here over one period equals zero, and this is what is called voltage second balance. So this is the first rule that we should remember and apply always, because if we have an inductor and we start switching the current in that inductor, the voltage across that inductor at steady state should equal zero, the average value of that. So we can now start talking about capacitor, and I think it's the same. We know the current in a capacitor in DC circuits at steady state will equal 0. So we have a voltage here, but the current at steady state equals 0 because the current depends on the in the variation of the voltage, and because there is no variation over time for the voltage, the IC will equal 0. But this is for non-switch DC circuits. However, if now we start switching this voltage across this capacitor to make variation, also the average current passing through that capacitor also will equal 0. So this is one of examples of switch capacitor voltage here, and this is the resultant current. Okay, and if we have this circuit, so in switching circuit, the average current passing a capacitor over a complete switching cycle in the steady state is 0. So this is the average current for the capacitor equals 0 over one period, and this is what's called capacitor charge balance. So these two rules are very popular and maybe the starting point for exploring and discussing or teaching the DC to DC converters. You have an inductor, it doesn't allow any change in current, but if you start switching on and off that current, it will generate some variation. That variation will produce a voltage, but the average voltage of that inductor will be 0. The same here, that capacitor doesn't allow the voltage to change, but if we start changing that voltage a little bit, the current average will equal also 0. So these two rules are very important and you should always apply them. So we are talking always about steady state and what will happen in steady state for the current and voltage for inductors and capacitors. And maybe this is a track of the current for an inductor. So as we see here, the current in the inductor is building up here, and this is during the transient while we are starting from 0 and we are going to a final value. So the value at 0 is different from the value after one period, and the value after one period is different from the value after 2 periods. Okay, and this happens in the transient, but at steady state we have different scenario where at start of a period we have some value, and at the end of that period we have the same value. So that's why we say the average of a voltage or current, it equals 0, as we explained for the inductor and capacitor, over one average or one cycle. And maybe this is the example of this is the current, but also that current will produce a voltage because voltage equal LdI by dt, and here the slope di by dt is constant, so that's why we have a voltage constant. This is rising or positive slope, that's why we have positive voltage, and this is negative slope, that's why we have negative voltage. If you calculated the area under this curve here or under this waveform and under that waveform, part of the waveform, it will equal each other, and finally it will equal 0 if you add them together. So this is what I want you to remember always, because this is the starting point for deriving the relations between inputs and outputs for DC to DC circuits. So our analysis in this part of module, we will discuss the steady state analysis, but not the transient. The transient has different routes of analysis and also different complexity and different objectives. We want what will happen after I run my system and passing the transient period. As we said, the pulsating current and voltage is not desirable for most of the loads, so that's why they start adding the capacitors and inductors, and we now agreed about how the inductors and capacitors should behave, because these are the starting point for analyzing our first converter, which is the buck converter. What is a buck converter? It's a step down converter. The output voltage here should be always less or equal to the input voltage. That means if you have an input voltage here of 100 volt, the output voltage should be between 0 to 100 volt. Now look at this topology here. We have the input source here, and we have a switch there. It's an IGBT, but it can be a BGT transistor or a Mosfet transistor. And we have a diode, and we have L and C. Why that diode and why that C, we will discover later. But the main thing that you need to pick up now is that switch is a high-side switch. And we talked about high-side switching or driving before, because the source here is not connected to the ground. So that's why when we drive it and we want to turn it on and off, we should have a driver called high-side driver. And we apply the PWM signal here, and we agreed that because it's a switching operated system and we want to get higher efficiency. So this is the topology of a buck converter. But we have a V input here, the voltage at the input side. What is the input at voltage at the output side? And is the duty cycle for the PWM, can it change the output side or no? To answer these questions, we have to go through two steps. And these two steps are common between all topologies we are going to study in this module. The first step is to analyze your circuit if the switch is on and if the switch is off. So in this circuit, for example, we have just one switch. That means that switch will receive an off signal, and that switch will be off, and I have to understand how the circuit and other parts of the circuit will behave during that off state, and then I will assume it has now turned on, and also I will make another analysis if that switch is on. I will make that for every circuit or every switch I have in my circuit, but in this circuit I have just one switch. So the first step is to understand how my circuit will be in the on time and how my circuit will be in the off time, and draw some relations and some calculations. After that, I have to combine these two analyses in just one general averaged analysis. And to do that, I have to recall again the voltage second balance rule and capacitor charge balance rule. We know the voltage, average voltage across the inductor will be 0. So that means that during the on time and off time, if I combine them, the average voltage over the total period time will be 0. So I can really combine them and equal them to 0. And that will give me the relation between the input and output, or input and other states and parameters in my circuit. The same if I have capacitor current, that current will equal also the average value of that will equal 0. And that also helps me to derive other relations. So these are the two steps that you have to really always understand how to start it, analyze the circuits, and also to apply. And that's why I summarize it like this for you. So now let's start with the first step for this buck converter. We have on-time analysis and off-time analysis. And for that, I have prepared for you these two circuits. We have a voltage input here, and it will push some input current, and that input current will go through the switch if that switch is on, and also it will be dividing here if it's allowed to divide to the inductor and also the diode, and it will reach the output. So we will assume in the first instance that the switch is on, and that on time will be for duration related to the duty cycle. So the on time will be delta t, and now in the on time that switch will be as a short circuit. We will not consider any non-ideal parameters now, and we will assume ideal parameters. So the switch, once I turn it on, I will assume it's a wire or a short circuit. Now let's understand how all the circuit, the other components in the circuit behaves if that is shorted. So I think you will agree with me that the input voltage here will push some current. That current now will reach that point, and that's high voltage, okay, and will reach that point. What will happen to this diode? I think that diode will be reverse biased because the cathode has higher voltage than the anode. So that's why we agree that it's off. So I think the circuit now is just an input voltage pushing current to an inductor, also capacitor. So you will agree with me that the input voltage here will push some current, and that current will go through the inductor and capacitor and will build some voltage at the output. Now, the input current, I think you will agree with me that it will be the same as the inductor current because it's not dividing at any node. Now, the question is we have to remember and apply the inductor rule and the capacitor rule. The inductor rule says that voltage across the inductor will equal the average voltage during the on time and off time will equal 0. So I have to prepare the value for the voltage during the on time. So what is the value of the inductor voltage during the on time? I think if I ask this question, the voltage across any component equals the voltage at the first node or the first terminal, subtracting from that the voltage at the second node. So what is the voltage at the first node here to get the voltage across the inductor? That voltage will equal the input voltage. Okay, so the first voltage here is Vn. What is the voltage at the second node, which is this one at steady state? At steady state, we have already built V output. So whatever the value of V output, this node is the same as V output. If it's 0, if it's 1, if it's 100, no problem about this, but we just know it equals the V output. So now VL at on time will equal V input minus V output. Okay, so now let's go to the off time circuit. And I think you will agree with me that this switch will be off. That means it's completely a cut. And that will happen during the other part of the duty cycle, 1 minus delta T. So that switch now is completely cut and there is no current will be withdrawn from the source. Remember, that means the current from the source, it's not always continuous. Okay, and that happened for buck converter. Okay, what will happen to the other part of the circuit? We know that we already pushed some current during the first part of the time of that period, okay, and that inductor will keep that current going. Okay, that inductor now keeps that current going in that direction and will go through the capacitor and will go to this node. There is no way to return back through this path because the transistor now is off. So there is no way for that current to go in that path, and it should go to somewhere else to return to the inductor and close the circuit. And that's why we use this diode here, because without this diode, you are going to prevent that inductor to push the current and complete the loop, and this will make the inductor spike and generate high voltage at that node and might damage the switch. So that diode now will work as a freewheeling diode that makes the inductor happy to return the current and makes a loop for it, a complete loop, and without discontinue the flowing of that current. Now that diode, if the inductor now will flow some current inside it, that means that diode is on. Okay, and I think we have now a different circuit from the first circuit, and we will ask the same question. What is the voltage across that inductor? And we will answer by looking at this node, and that node now the voltage is, look at this track, the voltage is 0 because now this track is 0. Okay, so the voltage here is 0, and what is the voltage at the other node? The voltage is still V output. So now the voltage across the VL or the inductor is 0 minus V out, and this is what we have here. Okay, now we got the VL in the on time and VL at the off time. How we are going to combine them? And I think the answer is by taking the average voltage. So we are recalling now the voltage second balance rule, which is the average voltage across the inductor for the full period, which is 1 over T integration from 0 to T VL dt, and we will equal to 0. So now let's start applying this rule. We have the integration, the first part of the integration over the on time from 0 to delta T, and the on time voltage equals Vn minus V out. I put it here. dt plus the off time period from 0 to 1 minus delta t, and that minus v out, and we will equal that equation to 0. After solving this, I think you will come up with Vn minus V out delta t, because the integration now is as a delta t, because this part is constant, okay? And the integration of that one is minus V out 1 minus delta t. And after equaling that to 0, we will come up with this relation. So V output equals the V input multiplied by the duty cycle you are controlling your switch. So this is the relation that we are heading to. But remember, this equation is a steady state input-output equation or relation. And what I mean by this, it doesn't tell us how the output changes from one value to another value. It doesn't reveal to us how this transient look like, but it just tells us the steady state value. If it reached 100 volt or 50 volt or 5 volt or 10 volt, but it doesn't tell us how it will behave during the transient. Because looking at the transient, we need different studies like small signal modeling, and that small signal modeling is a little bit advanced topic and will generate finally something called a transfer function or state space model, which all will have some relations with the frequency domain and time domain that will describe for us how the system will behave. Is it overshooted or underdamped or overdamped, and these things. But this is not part of our module. And that small signal modeling is needed if you are looking at designing a controller or feedback system. Like, for example, if you want a V output and that V output you want to regulate it regardless of the output current or output resistance or load. So in that case, you are going to get a feedback from the V output and design some controllers like PID control, for example, and return that as a control signal for the duty cycle for the PWM. So the small signal modeling and these things are quite useful and needed if you are heading to control your circuit or to provide some control. However, in this part of the module, we are just heading to understand the steady state relations between inputs and outputs. From that equation now, we understand that the steady state relation is a linear relation that's controlled by just the duty cycle. It doesn't depend on the inductance value or the capacitance value. And now I will stop the video for this part and will continue talking about all the signals for all components in the coming video. So thank you.